All right, this is Unit 8, Lesson 7, Part 2. So we are just going to pick up where we left off on the bottom of this page. We're going to do number 5, and I'm going to keep flashing back to that 5-step process that we had in the last part of these notes. So number 5, step 1 is to simplify the function, which means doing any factoring and canceling that we need to do. So this one right here, this is we can do the slide and divide method because this is a 2 that doesn't divide out of everything. So we're going to multiply it down to the end. We will start with that. So multiplying the 2 times that 1 at the end, and then we'll factor it down. The denominator is ready to go, so I'll factor that right now. X squared goes down to x times x. Multiplying to a negative 12, adding to a negative 1 would be a minus 4 and a plus 3. So I can start with that. The numerator, I can start by factoring that down. I'm going to squeeze it in along top here. So I'm multiplying to 2, negative 2, and adding to negative 1. So that'd be an x minus 2, x plus 1. And then these denominators, nothing to do there. So then finally we take the 2 that was here before and divide both of these things by 2. Okay, so let me rewrite that. So 2 divided by 2 reduces down to 1, so I have x minus 1. 1 divided by 2 does not reduce, so the 2 comes back to the front, and it looks like that. Then my denominator. So there's lots of factoring that happened, but there was actually no canceling that happened with this one, because notice there are no common binomials that I can eliminate. So I simplified it, but that's about it. So step number 2. Step number 2 says find the x-intercept by setting the numerator equal to 0. So I have 2 separate pieces in my numerator, which means I'm going to have 2 separate x-intercepts. So that's why I included this one, to make sure you can see that that is in fact possible. So I take x minus 1 and set that equal to 0. I take 2x plus 1 and set that equal to 0. So here, if I subtract 1, I get x equals 1. So I'm going to plot that right here, and I'm going to write it as an ordered pair. 1, 0. I can also set this one equal to 0. So I would subtract this 1 and then divide by this 2. So negative 1/2. And you can just approximate where that decimal would be right there and write it as an ordered pair. Negative 1/2, 0. So 2 different x-intercepts. They happen to be very, very close together. Next step, step 3, find the vertical asymptote by setting the denominator equal to 0. So vertical asymptote, we have 2 pieces in the denominator, which means we're going to have 2 vertical asymptotes. That has not popped up before, but it is very possible. So I take that and set it equal to 0. Take this and set it equal to 0, and I am going to get 2 different vertical asymptotes. So for this one, I add 4 and I get a positive 4. So I have 1, 2, 3, 4. And I can write that here, x equals 4 is one of my vertical asymptotes. And then this one, subtract 3 from both sides, and I get negative 3. So that's is my second vertical asymptote, and I can write x equals negative 3 right here. Step 4, find the horizontal asymptote using the rules below. So we have a degree of 2 in the numerator, a degree of 2 in the denominator. So that is this third rule where we use the leading coefficient of p over the leading coefficient of q. So my horizontal asymptote, it is y equals the leading coefficient of p, which is 2, over the leading coefficient of q, which is technically a 1 in front of that x squared. So 2 over 1 gives me a horizontal asymptote of 2. So I will plot it. I will write it down. And then we move on to our final step before we graph, which is to identify any holes. Holes occur when there's a common factor that canceled out. No common factors here, which means no holes. Okay, so now just like in the previous part of this lesson, we're using Desmos to give us a little guide as to what the graph actually looks like. So let me delete the last one I have on here. Okay, so numerator, 2x squared minus x minus 1, and then make sure we separate that out, divide, and then in the denominator we have x squared minus x minus 12. Okay, so very interesting looking graph here. You can see we've got 2 vertical asymptotes, 1 horizontal asymptote. These points that cross over the x-axis happen very close together. You can barely even see that it's 2 separate points when you zoom out. So that's the shape that we are trying to plot. We have kind of a little boomerang shape here, over here, and then something that almost looks like a parabola down here. Okay, so our graph looks something like that. Finish it off with the domain and range. So the domain x can be anything but any vertical asymptotes that we have, which would be 4 and -3, and then any holes that we have, which is none. So there's nothing to add there. And the range can be anything but the values of the horizontal asymptote, and then any values in the hole, which is nothing. So those are all of our characteristics for number 5. All right, so I want to look at number 6. This one's going to be an interesting shape. So step 1 is to simplify any factoring and canceling that we can do. So the numerator, I can factor out a common x squared, and that leaves me with an x plus 3. And then the denominator, this is a quadratic, so I'm going to factor it down, x times x. And if you look at the numbers, they're supposed to multiply to a -3, and they're supposed to add to a +2. So that would be a +3 and a -1. So simplifying involves canceling anything that we can. These common binomials can eliminate. So that is going to be part of a whole, which I will get to in a moment. Step 2, find the x-intercept by setting the numerator equal to 0. And in a case like this, you want to make sure it's the reduced version that you're using. So it's only the x squared that I would set equal to 0. And there, because it's an x squared, we take the square root of both sides, and because it's a 0, we don't need the plus or minus. It's just x equals 0. So I write it here, I plot it here, and I write it here, making sure that it's an ordered pair when you list it there. Step 3, find the vertical asymptote by setting the denominator equal to 0. And again, make sure it's the cleaned up version over here. So vertical asymptote by setting the denominator, just the part that's left, equal to 0. So here we would add 1 to both sides, so we end up with x equals 1. So I write it here, I plot it here, this would be a little dotted line, and then I can write it here and make sure this gets written as an x equals, like a line, not an ordered pair. Step 4, find the horizontal asymptotes. Check our degrees. Degree of 3 in the numerator, degree of 2 in the denominator. So that puts us into this first category right here. The degree of P is larger, because it's a 3, than the degree of Q, which is a 2. So there is no horizontal asymptote. All right, and then finally, the idea of a whole. So a whole happens if you have a common factor that canceled out. So to find the x coordinate, and this is on the previous page, set the common factor equal to 0. So we're going to take the guy that canceled here, the x plus 3, and we're going to set that equal to 0. So x plus 3 equals 0, I would subtract 3 from both sides, and that will be the x coordinate of the whole. The rest of it comes from taking that -3 and plugging it back into the reduced version. So numerator is an x squared. If I take -3 and square it, I get 9 over. And then the denominator is just that x minus 1. So x is a -3 minus 1 would be a -4. So I get this lovely value here, a nice -9/4. Or if it makes you feel any better, that would be -2.25. But you can plug that in and find out so you know where to plot it. So let's plot that point as well. -3, 1, 2, 3, and then -2 1/4-ish. So right about there. All right, so that is everything that we have so far. I'm gonna put this into Desmos so you get a picture of the graph. Desmos is not cooperating with me. Sorry, one second. All right. reset it there. All right, parentheses for the numerator. The numerator is x. That is not working at all. Good, really good. Okay, if this doesn't load back up, I'm just gonna have to show you what it looks like. Yeah, nothing's typing for some reason. All right, so what it looks like, and you can go right ahead and plot it into Desmos yourself if you'd like to. Part of it looks kind of like a line. Like this comes up like it's gonna be a linear function. Oh, and this is supposed to be a hole. I forgot to plot it like that. Sorry, that should be a hole, not a closed dot. Comes up like it's gonna be a line, and then it just shoots down like it has a vertical asymptote. So same thing happens as it comes in from the other side. All right, so it comes in as if it's gonna be a line, and then it gets to a certain point, turns around, and then glides like that. Okay, so our graph looks something like that. Domain and range. Domain x can be anything other than the vertical asymptote and wherever the hole is, the x coordinate. So that's the domain. Does not hit this x coordinate, and it doesn't hit this one either. It's supposed to be an open circle. I did a terrible job with that, but that's what's supposed to be there. And then for the range, y cannot equal the horizontal asymptote, which we don't have to worry about, or the x coordinate of that hole. Notice every other y value ever gets covered. We just don't have the value of that hole right there. And this is not helpful since I don't have Desmos. But see that we're actually missing this chunk of y values right here. This point right here, and then this point right here. So it's 0 and below. So we can say y is everything less than 0. And then if I had Desmos, I could show you the actual point right here. It's actually supposed to be at 1, 4. I didn't do a great job of estimating that. It's supposed to be up here. So it'd come down, hit this point, and then go off. So this point right here, 4, is kind of like a little minimum. So it could be anything above 4. So sometimes the range gets a little bit tricky. I wanted to make sure I showed you one that was quite tricky. Let's see, last thing that we are going to do. Let's do number 8. Number 8 will be our last one. Step number 1, simplify. Simplifying for us means factoring. So the numerator factors to x times x to get the x squared. We're multiplying to a negative 28, adding to 3. So that would be a positive 7 and a negative 4. Denominator, we have an x squared as well, so start with x times x. This one, it's supposed to multiply to 35 and add to 12, and that would be 7 and 5. So in simplifying, you'll notice that these guys cancel, and then let's run through the rest of our steps. Step 2, find the x-intercepts by setting the numerator equal to 0, so just the part that's left. When I set that equal to 0, I can add 4 to both sides. Go ahead and plot that as an x-intercept and write it down over here as an ordered pair. Next, step 3, find the vertical asymptote by setting the denominator equal to 0. So just the x plus 5 that's left, that gets set equal to 0. And then we solve for x. Subtract the 5 from both sides. So I am going to plot that and write it over here. All right, last thing we need to do right now is our horizontal asymptote. Check the degrees real quick. That's a degree of 2, that's a degree of 2. So when their degrees are equal, we take the leading coefficient of p over the leading coefficient of q. All right, so leading coefficient of p is like a 1x squared, and this is also like a 1x squared. So our horizontal asymptote is just y equals 1. So I will sketch it right here, write it over on my list. And then finally I have the whole. Okay, so the whole comes from the common canceled factor. For the x coordinate, I take the canceled factor and I set it equal to 0. Subtracting 7 will leave me with a lovely negative 7. That's going to start off the whole. Negative 7 comma something. All right, and then that negative 7 gets subbed in here. That's how I figure out what the y coordinate is supposed to be. So the y coordinate, I sub the negative 7 in here. Negative 7 minus 4 is a negative 11 over negative 7 plus 5 ends up being a negative 2. Okay, so when I divide this out, I get 5.5. a lovely 5.5 that I can put into an ordered pair. And that goes with the -7. So you can plot that. So this is -5, -6, -7, and it's at 5.5. So 1, 2, 3, 4, 5.5. Like that. Okay, domain and range, let's do that really quickly. X can be anything but the vertical asymptote and the x coordinate of the whole. Then the range, let's see what our sketch looks like first. Pull Desmos up and see if it's working yet. I feel like it's not. Oh, there we go. All right, x squared plus 3x minus 28. Divide that by x squared plus 12x plus 35. So that is what our graph looks like. You can see our vertical asymptote or horizontal asymptote. This just kind of seems like the classic boomerang shapes, like this. Okay, range, nothing special is happening here. There isn't a big gap. Y can be anything but the horizontal asymptote and that y coordinate of the whole.